Hello, my name is Ana Maria Bratu. I work at the National Institute for Laser Plasma and Radiation Physics. And my talk today is about the engineering laser system for defense application. More precisely, we use two different laser-based spectroscopic methods for identification of hazardous substances that are used for improvised explosion devices or homemade explosives fabrication. So I will make a short introduction about hazardous substances. Then I will present the methods used for their identification, some characterization of materials, results, and conclusions. So hazardous materials are substances that are dangerous to human health or environment, and we can find them in our home, in our work places, or in industrial or areas. The most common hazardous substances are flammable liquids that are used by terrorists to make improvised explosive devices. Okay. Some systems that are used to identify them must be sensitive and accurate, must detect many types of chemical agents, and must detect low analytes, must have a low analyte detection limit, and must be operationally easy to use with minimal training and low cost. Laser-based spectroscopy methods, due to their high sensitivity, selectivity, and multi-component detection, create a solution for identifying and characterizing explosive materials in the fastest and easiest way possible. So the purpose of the study is to use two spectroscopic methods for identification of 8 substances. Benzene, toluene, acetone, and ethylene glycol were identified using CO2 laser photoacoustic spectroscopy in the region between 9.2 and 10.8 micrometers, and ammonium nitrate, potassium chloride, nitrobenzene, hexamethylene tetramine spectrum were determined in the terahertz region between 0.1 and 3 terahertz. Benzene, toluene, acetone, and ethylene glycol are solutions that are flammable, but they are not directly explosive. But when they are mixed with other substances, they can become or can help to the production of improvised explosive devices. For example, acetone with combined with hydrogen peroxide may produce an explosive compound, 3-acetone triperoxide. Powder substances like ammonium nitrate is very used in as fertilizers, but is also the most common compound used in improvised explosive devices. potassium chloride, nitrobenzene, and hexamethylene tetramine are also principal precursor for explosive devices. So for benzene, toluene, acetone, and ethylene glycol, we use CO2 laser photoacoustic spectroscopy system. This system is used to identify these substances because of the tunability of CO2 laser that help us to realize photoacoustic spectrum of these substances and to see where is the maximum absorption. So the main components of the system are the CO2 laser and the photoacoustic cell. The CO2 laser is tunable on more than 54 laser lines, depending on the rotational vibrational transition, and the gases are detected in the photoacoustic cell. The laser power emits power between 0.5 and 5 watts in the spectral range of 9.2 to 10.8 micrometers on the 4 branches, 9R, 9P, 10R, and 10P. So how is this process made? The laser radiation is amplitude modulated by a mechanical chopper focused by selenium zinc selenium lens and introduced in the photoacoustic cell where the gas is presented. A part of the radiation is absorbed by the target molecule and is excited on the rotational vibrational states. The non-radiative desactivation of the molecules produces an increase of temperature inside the resonator and a variation of pressure that is an acoustic wave in the resonator. So by tuning the laser at different laser lines, we have different photoacoustic signal. The acoustic waves is recorded by 4 sensitive microphones placed inside the resonator, and the acoustic signal is converted into electrical signal and transferred to a lock-in amplifier. The laser power inside the photoacoustic cell is considered constant, and after passing to the photoacoustic cell is recorded by a power meter. The values of the power and the signal from the lock-in amplifier are collected to a data acquisition interface and transferred to the computer. So before we start to identify our samples, we measure the background signal of the system, and in pure nitrogen, and the signal, the background signal is about 35 microvolts. For measuring our samples, we use 0.1 milliliter of solution. that we transfer to an absorbent paper and put it in a glass cuvette and we let them to evaporate for 30 minutes at room temperature. After the solution evaporated, we introduce them in the photoacoustic cell, and then we tuned our laser on each laser line. First, we do the photoacoustic spectrum of the air to see the difference between the air and our solution. So here you can see the absorption spectra of benzene that present maximum absorption at the line 9030 that corresponds to a wavelength of 9.636 micrometers. This benzene presents a very particular absorption at this line. For toluene, we see that presents 4 peaks of absorption, but the maximum value was found at 9028. That corresponds to a wavelength of 9.618 micrometers. Acetone, the spectrum of acetone present a high absorption at 10p20 that corresponds to a wavelength of 10,588 micrometers. And this is the spectrum of ethylene glycol that prevents a high absorption at 10R8 line. That means 10.330 micrometers wavelength. This solution were identified using CO2 laser photoacoustic spectroscopy. The powder substances were identified using terahertz time domain spectroscopy. This is a schematic of the system. We use terahertz equipment from Expla, and as a pumping source, we use erbium-Young laser emitting at 780 nanometers with a pulse duration of 70 femtoseconds. Here you can see the probe placed between 2 antennas and the detector, and the spectrum of the substances is realized in the transmissions mode. This is the laboratory equipment that is connected to a computer with a LabVIEW program. So the transmission spectrum of the substances, we can see that ammonium nitrate present 2 significant peaks at 2.4 terahertz and 3.5 terahertz, which constitute the unique spectral signature of the compound. Potassium chloride has a transmission spectra at 2.5 terahertz. Dinitrobenzene emits a maximum 2.4 terahertz, and hexamethyl tetraamine has maximum at 20.3 terahertz. If laser photoacoustic spectroscopy is an mid-infrared method. Terahertz spectroscopy is far infrared method. So we can say that we identify substances from mid-infrared to far infrared spectrum. In conclusion, we identify 8 substances using 2 laser-based spectroscopic technique. Benzene, toluene, acetone, and ethylene glycol presented a special absorption in the CO2 laser lines. Further application for this compounds is to calculate or to realize the detection limit of this that these substances have to the CO2 laser photoacoustic spectroscopy. And ammonium nitrate, potassium chloride, nitrobenzene, and hexamethylene tetramine were identified in the terahertz region. This terahertz time domain spectroscopy can be used for detection of these substances in packaging or containers. The 2 techniques reveal the different characteristic spectral patterns for each substance, and we can observe different spectral behavior. The use of these 2 techniques to identify as many hazardous substances as possible is important for human security, defense, anti-terrorism, and smuggling by recognizing the spectral signature of the hazardous materials. So thank you for your attention.
Kind of modern applications.
Yes, and sorry, I'm very emotive.
What kind of applications your study can have?